So a summary of what we've got sorted out so far is that as the wave passes, remember it started here, moved along, moved along, and moved along. As the wave passed, an element of string, first it rose and then it fell. We said that the height of that piece of string, or an element of string, we're going to call that d, and that height depends on two things. It depends on which point we picked horizontally, and it depended on what time it is. So the height is a function of position, horizontal position, and time. And this height d is always measured relative to the equilibrium position. So now we're going to move on to asking, how do we find that height as a function of x and t? How do we find an expression for it? How do we find an equation for it? So something we can do is we can find the height as a function of x. So what does this point do? And we can find what this height does over what this point does over time, and we can also find out what does the whole thing do over distance. So if we find those two expressions, then we can combine them. So what we mean by that, let's get that simulation out again and see if we can get a clearer picture of what we're talking about. I'm going to go low tech here. I'm going to try and film my laptop screen. Oh yeah, that's not bad. Okay, so here's that wave on a string simulation. And when we were looking at it, we hit play, and the wave was going up and down. So if we ask what happens, whoops, there goes my slide. So how do we find d of x for constant time? What that means is that we pick one single time, so we hit pause, and we ask what is the height of the string as a function of x. So that's what that means. That graph is called a snapshot graph. Okay, so it's what does it do as a function of position for one single time. The other thing we can do is we can ask, what if we pick one position of x, let's just pick this green dot right here, and ask what does that one single position do as time changes. So we can ask about that as well. So that kind of graph is called a history graph. So this is what happens at one time, this is what happens at one position. Then we're going to put those two expressions together, and we're going to use those two combined expressions to find the complete expression as a function of position and time. Okay, that's where we're going with this. So the first thing we have to do now is ask, before we can write an equation for d, is ask what kind of wave are we looking at anyway? So what we're going to do, because everything we've done so far applies to every kind of a wave, now we're going to narrow in to one particular kind of wave. And the one particular kind of wave we're going to look at is called a sinusoidal wave. Just to go back to that simulation for a second, if we look at our source, so this is our source right here, this is what's making the wave. That's moving up and down with simple harmonic motion. That makes this a sinusoidal wave. And these are the kind of waves we're going to look at for the next little while. And we're going to do lots of work on those because it turns out those kind of waves are really important. Two kind of sinusoidal waves, which is really important to kind of life as a whole, are sine waves and sound waves and light waves. Both of those are sinusoidal, and we use those to take in a lot of information about our world. So those are really important to study and to be able to understand. Okay, so we're going to look at sinusoidal waves, and a sinusoidal wave is just a wave made by a sinusoidal oscillation. So we're going to look at those two graphs that we defined, the history graph and the snapshot graph, and we're going to write down expressions for those, and then we're going to put them together. Let's start with the history graph. So let's start with the history graph. And remember, the history graph is when we looked at one green dot and asked what did that do over time. So a single green dot over time will move with simple harmonic motion because the source moves with simple harmonic motion. So that tells us that the height of the one single element that we're looking at so the height for one element is described by simple harmonic motion. So that one bit of string moves with simple harmonic motion. So SHM for simple harmonic motion. And it does that as a function of time. When we look at that wave, this should be a little bit familiar from the end of what you did in Physics 1050 or Chapter 15. And there is extra review material posted. There was that little tiny bit from Lecture 1, and there's even more detail under the review section on D2L if you're looking for more. So some of the things that we talk about with simple harmonic motion, the highest point on a wave, that's called a crest. The lowest point on a wave, that's called a trough. And this height goes up and down over time. And the amount of time it takes to go from one crest to another crest, so for the green dot to be at an amplitude, to go all the way down and come back up, that amount of time is called the period. Okay, so we already did that with review. Something moving in simple harmonic motion or a sinusoidal wave means it can be described by a sine or a cosine. In Chapter 15 we used cosine. For traveling waves it's more typical to use sine. Either one is legitimate, but I'm going to stick with your textbook which uses the sine notation. So the height of one element as a function of time has some maximum value a, the amplitude, changes sinusoidally, so we'll describe it with a sine function. It changes with a characteristic time of t, so our sine function will be 2 pi over t times the time, plus some phase constant phi naught. And this was also written as a times sine omega t plus phi naught. So that's all pretty familiar from Chapter 15. Omega 2 pi over t, why don't we get that in here? And if you remember that t is 1 over f, could also be 2 pi times frequency f. That's called the angular frequency. And that's measured in units of radians per second or just seconds to the minus 1. And then phi naught is our phase constant. And what the phase constant does is we know that a sine wave normally starts from 0, but an oscillation doesn't necessarily have to start at 0. It could start from somewhere in the middle, or the amplitude, or the negative amplitude. This phi naught allows for a different starting point, and that's what we talked about in the recap from Chapter 15. Okay, so this is our history graph. That green dot moving up and down over time can be described by this equation right here. Okay, what about how it moves at one instant in time? So what does the wave look like along the entire length when we hit pause? Let's do that part next. So this bottom graph is called the snapshot graph. So this is where we hit pause and we look at the wave as a function of horizontal position. So what does it look like along the whole length of the wave? Well, in this graph, why don't we even just get that popped back up here, just in case you forgot. So here's that wave. So as a function of position and time, it's doing this. If we want a snapshot graph, we hit pause. And we see that this is also described by a sinusoidal function because our source moves with simple harmonic motion. Okay, so for the whole length of the wave, what it looks like at one moment in time along the whole length is also simple harmonic motion. So for this graph, d for one point in time that also has simple harmonic motion. So SHM for simple harmonic motion as a function of position. So if that moves with simple harmonic motion, it means it can be described as a sine function. So let's write that equation down. So d. So if we're going to describe that by a sine function, d is going to have some maximum value. Still going to be the amplitude. That stays the same whether we've hit pause or not. So d has a maximum value of a. It varies as a sine. Okay, now let's be careful here. This graph repeats over distance. So if we look at one peak to the next peak, that happens over a characteristic distance. Here it happened over a characteristic time. Here it happens over a certain length. This length right here is what we call the wavelength. So our sine function repeats in length. So when we write down our sine function, we write 2 pi over lambda. So here, t is the period, the time to go from crest to crest for one point. Here, lambda is the distance to go from crest to crest at one time. So our sine function has a maximum value of a times sine 2 pi over lambda. This varies with respect to position x, and it would still have the same phase constant. Let's write down our definition of lambda. Lambda is called the wavelength. It's a distance, so it's measured in meters, and it's the distance for one cycle, or the length of one cycle. Up here, we said 2 pi over t was omega. We can do the same sort of deal down here. Down here, we say that 2 pi over lambda is called k. Up here, omega is radians per second. Down here, k is radians per meter. So k has a name. K is called the wave number. And the units are either meters to the -1 or radians per meter. Omega, our angular frequency, that was the number of radians our oscillator goes through every second. K, our wave number, is the number of meters it goes through, the number of radians it goes through every meter. So how many cycles are in 1 meter. So that's our description with respect to time. That's our description with respect to x. The last thing we might toss in here, just to put it here because it seems to fit reasonably well, is what about our wave speed? So this wave is moving to the right with speed v. So v is the wave speed. Wave speed is how far that bump travels over time. So we could calculate it as distance over time. The distance for one cycle is lambda, and the time for one cycle would be the period. So our wave speed can be given as distance over time. If we think about one cycle only, that's lambda over t. We remember that 1 over t is frequency. So the wave speed, how fast that bump travels down the line, is the frequency times the wavelength. And sometimes that's called the wave equation. I often say that in 20 years, the one equation you should remember about physics is F equals ma. For this course, I'm going to throw in that the other equation you should remember about physics in 20 years is that F equals v that v equals f times lambda. Okay, so now there's that part done. So we've described what happens over time. We've described what happens over distance. Our next part is to put together what happens when we put those two things together. How do we combine those two notions? How do we combine those two descriptions to get the complete description? So we're going to stay with our sinusoidal waves. We're going to have our wave moving to the right with speed v. So that's the kind of wave we're going to look at. We could also do this description with a wave moving to the left, but we have to pick one, so I picked to the right. So let's put our wave speed in on this picture, moving to the right with wave speed v, where v would be equal to f times lambda like we discussed on the previous slide. So to begin to combine, let's start with what does our wave look like at time t equals 0. So what does the entire wave look like as a function of position if our t equals 0? And let's say that this picture applies to t equals 0. So this is the snapshot right at the initial time. So d of the whole wave at time equals 0 is given by a times sine of 2 pi over lambda, or k, times x plus the phase constant phi naught. So all I really did here was write down this equation, and I said the time we're specifically looking at is time t equals 0. Okay, that's our starting point. So this is our first wave. And why don't we even trace that guy out? So this is at t equals 0. Just going to highlight that in pink. And if we need a reminder here, we can put this in. So A is the amplitude. 2 pi over lambda means it repeats every wavelength, so this part is our wave number k. And then phi naught is our phase constant, which means our wave doesn't have to start at t equals 0. These terms are probably new to most of you, so it doesn't hurt to say them a couple of times over. Okay, so next, our wave is moving to the right with speed v. That means a little bit of time later, the wave has moved to the right by a little bit. So let's draw that wave now a little bit of time later. So this wave right here, this dark blue one, that was just copied from above. So this dark blue one is t equals 0. A little bit of time later, it moves to the right. Oh, that's my phone ringing. I'll call my mom back after. So a little bit of time later, it moves to the right. So let's draw that wave shifted over to the right by a little bit. Because that's what happens over time, is it moves to the right. So this wave, the one now drawn in pink, is for t greater than 0. It's moved forward a little bit. So how do we write the equation for this wave? It can't quite be this one because it's not exactly the same. It's changed by a little bit. And we know that the height of this wave is going to depend both on the horizontal position and the time. So our next thing we're going to try and sort out is for this bottom wave, what is d as a function of position and time to get the complete description of the wave on the string? Well, one thing we might notice, if we pick one spot on this wave, so let's pick, I'm going to grab a brighter color. Let's pick this spot on the t greater than 0 on the pink wave. So for this spot, it has horizontal position x, and it has time t, and it has some height d of x and t. So this is the height at position x at time t. Is there anything we notice about this spot? Well, this spot is exactly the same height as this spot. So let's just draw a dot here. Those are exactly the same height. So that's something that we see. So let's add that note here, that we see d of x and t is exactly the same as the point on the wave, same as, the point on the wave at t equals 0, which is a little bit of distance behind. What can we call that distance? Well, let's call that distance delta x, and let's put that on our picture, which is delta x behind it. How could we figure out how big delta x is? Well, the wave is moving to the right with speed v. We know it's moved an amount of time t. We know that speed is distance over time, so v is delta x over t. So this delta x is v times t. So this point is the same height as this point, which is a distance delta x behind, and delta x has to be v times t. There's a relationship we can see just by looking at what the wave does over time. Okay, let's use this and put these two guys together and see what we get for our expression. So d of x and t, which is what we're trying to figure out, is equal to this wave, which is behind that one. Okay, so let's write that down. So d of x and t is the same as the height on this wave, which is a little bit behind. So it's d of x minus vt, so that same point that's a distance vt behind, at time equals 0. Typically when we write this down, we just don't bother to write down the comma 0. So if we don't have a t put in brackets, it's just kind of implied that it's at t equals 0, so we normally just write it this way. So what this means is to get the equation for this wave, all we have to do is put x minus vt in this expression, because we know they're the same except this x is smaller by an amount v times t. So let's put that in. So that's equal to the amplitude times the sine of 2 pi over lambda times x minus vt plus phi naught. Okay, this is our expression. We can leave it like this, or we can make it just look a little bit nicer. Let's multiply out these terms. So we've got 2 pi over lambda times x minus 2 pi over lambda times vt plus phi naught. Okay, this is looking pretty good. There's a couple of things that are standing out here. This part, 2 pi over lambda, that's the wave number k. So we could put that in. This bit right here, v over lambda, that's jumping out as belonging to the wave equation, where the wave equation says v equals f lambda, which means that v over lambda equals f, and 2 pi f, that's the angular frequency omega. This expression is for our wave moving to the right. So the equation of motion, or the height of the wave at horizontal position x and time t moving to the right with speed v, is this expression right here, but I'm just going to write it down a little bit more nicely with k and omega in there. So d equals a times sine of kx minus omega t plus phi naught. And that's a wave moving to the right with speed v, where v is given by omega over k. If we wanted to, we could go through and we could do this whole thing again for a wave moving to the left. what we would see is that this wave would be to the left of this one, and our result would be is that d is equal to a times sine of kx plus omega t plus phi naught. There would be our equation for a wave moving to the left. So if I ask for the equation of motion for a traveling wave, what I'm asking for is this equation, and you'd have to be careful with your plus and minus here. Minus means the wave is moving to the right, and plus means the wave is moving to the left. So there's our equation for our traveling wave. The last little bit that we're going to put in here now is our wave equation. We know v equals f times lambda. And let's put in that f is equal to omega over 2 pi. Let's put in that lambda, since 2 pi over lambda is k, lambda is going to be 2 pi over k. The 2 pi's cancel, and we're left with omega over k. So the first time we wrote down the wave equation on the previous slide, we said v equals f times lambda. Sometimes you know omega and k instead of f and lambda, so it's also equal to omega over k. So there's the full form of the wave equation, which is handy to have in case you want to use it. So the next thing we're going to do is an example. I think this video has gone on long enough, so we'll go to a fresh video for our example.